Thank you. Thanks. Thank you. It's an honor and a privilege to talk in this room. So thank you for coming and helping make it possible. And thank you for joining me on what's a very exciting day for me, at least, which is the day that my new book, Our Accidental Universe, has finally hit the press. And so that's our topic this evening. It's a set of stories of how astronomers actually make discoveries and how we find out about the cosmos. And this is really important to me because I think, especially when speaking in venues like this, on stages like this, it's quite easy to give the wrong impression. It's quite easy, I think, to give the impression that we know what we're doing. And this is sort of played into by the way that we teach science often. You know, science is, to some people, a method for testing hypotheses, right? What we do is we all sit around, we think hard, we come up with an idea, we work out a way to test it, we run to our laboratories or our telescopes, we test it, we say, yes, we were right, and then we spend the rest of our careers telling our colleagues that we were right, and maybe writing books that say we were right, and things like that. And actually, that's not the fun bit at all. It almost never works like that. Actually, science progresses in a chaotic fashion. Astronomy in particular progresses based on a series of accidents, things we stumble across in the cosmos, things sometimes that visit our solar system unexpectedly or which turn up in telescopic images that we weren't expecting. And those moments where you don't know what you're seeing, those moments where you don't understand what's going on, those moments where you stumble over and are surprised by a new idea, those are the fun bits. And I think that by thinking about those surprises, those happy accidents in studying the cosmos, it really helps us think about our place in the universe. So, for example, we should think a bit about how to think about beings that exist in a universe, not just on a planet. It is possibly the worst picture anyone's shown at the Royal Institution, which is rather nice. It's a shot of a night sky just after sunset. There's a horizon without much definition to it, a few hills in the distance. And the sun has just set, and I don't know if you can see on the screen, but there's an evening star in the sky. If you were outside tonight and it was clear, this is perhaps the view you might have had with Jupiter, low in the west at this time of this year. In this case, if we zoom in, turns out that star is double. There are two stars there, and that's because this is a shot not of an earthly landscape, but of a landscape on Mars, taken by a Mars rover that landed there. And that evening star in the sky isn't Jupiter, it's the Earth with the moon next to it. And so we have this really wonderful, I think, juxtaposition of something very banal. This is a terrible shot of an evening sky, and something really profound, which is seeing our planet reduced to Carl Sagan's famous pale blue dot. And I think there's lots more to say about this image, but one of the things I want to draw out this evening is no one built a Mars rover, spent billions of dollars sending it to Mars to land, to look back at Earth. It's there because we want to study Mars for all sorts of good reasons, and indeed we could be surprised by Mars, which turns out to have a richer history than many of us suspected 10 years ago. But we also get these lovely side effects that teach us about the universe and our place in it. And actually this theme of accidental discoveries is particularly prevalent in spacecraft as they've gone and explored the solar system. So I thought I'd start with my editor's favourite story, the one we kept coming back to in the book. And it's a story about this place in the solar system. So this, of course, is Saturn, the show-off planet, the planet with the rings. And it's been an object of fascination and study for hundreds of years. Well, longer than that, really, but since Galileo discovered the ring system using the first astronomical telescope. And Saturn was visited by the Pioneer probes in the 70s and then the Voyager probes, which flew past. But really, a planet of this complexity, a place that has some of the solar system's fastest winds, a place that has gas dynamics in an atmosphere that's so complicated that we still don't quite know what the length of a day is on Saturn. A place that has these magnificent rings made up of millions of icy particles arranged into these incredibly thin structures. The width of the rings is is smaller than some of the buildings around us here in the centre of London. It's no more than a couple of stories, and yet they're there and apparently long-lived. And a place that has a retinue of moons, including one Titan, which is the only moon in the solar system that has an atmosphere, a thick atmosphere of nitrogen, methane, and much other complexities as well. We needed to send a probe there to tour the system, to spend time there, not just fly past, but to visit. And that was the Cassini probe, which was launched from the space shuttle and got there in the early 2000s. And Cassini was built to study the planet, to study the rings, to study Titan. But on its way in, it went past a moon called Enceladus. Now, Enceladus had been discovered more than 100 years earlier. It's one of the larger moons, but it's fairly nondescript. This is the best image that existed before Cassini got there. This is a shot from the Voyager spacecraft, and you can see it's an icy body. The size, it's about the size of the British Isles. So it's a small bit of icy rubble, a leftover, presumably, from the early days of the solar system, from the time 4.5 billion years ago where the planets were forming, captured by Saturn, and in orbit around it ever since. And we can make it look good. You know, here's another early image of Enceladus, and all right, if you put it with Titan there and the rings in the background, it looks great, but it's essentially just an ice cube in orbit around Saturn. And it was coincidence that on one of the early loops that Cassini took around the Saturn system, it happened to be going past Enceladus. Most of the team were focused on studying the planet itself, on studying the upcoming encounter as it swoops around the planet and around the rings. And so on that first flyby of Enceladus, no cameras were turned on, and most of the instruments were not taking data. The teams were busy getting ready for what was to come a few days later. The one exception was a team behind an instrument which lived on a long boom that stretched out away from the Cassini spacecraft, an instrument built and run by a team at Imperial College London by Michelle Doherty and co. And their instrument studied the magnetic field around Saturn. They were interested in the planet's magnetic field. We know that Saturn has aurora, it has northern lights and southern lights, just like the Earth does. And we know that that magnetic field interacts with Titan's atmosphere. And so Michelle and co. thought they'd use the Enceladus encounter as a dry run, that they'd check that their instrument recorded no change as it flew past a small inert ice cube, what should have no effect at all on the magnetic field. And when they came to analyze the data, they were surprised to see that there was a change, that something near Enceladus was affecting the magnetic field of Saturn. In other words, there was some activity there, that something was happening around this moon. They went and talked to their colleagues who were running the other instruments on the mission, and it was agreed that they would take a closer look at Enceladus. And they flew back over the moon's south pole, passing just a few hundred kilometers, I think, above the South Pole, with cameras on this time. And what they discovered was completely unexpected. What they discovered was that Enceladus has fountains, that from its South Pole, water is shooting up into space. And they'd just given their spacecraft the first interplanetary bath recorded in human history. They never went back this closely again because it's presumably quite dangerous for a spacecraft with sensitive electronics to fly through a car wash, even one provided naturally in the Saturnian system. But this is a remarkable discovery. We have water flowing from a moon that should be frozen. That means that underneath the icy surface, there's presumably an ocean. Later experiments, as Cassini went back to Enceladus, which became a focus of the mission, later experiments showed that the water was salty, which tells you that there's not just an ocean, but there's an ocean floor down there, a place where water comes into contact with rock, a place that begins to feel a bit like the places on Earth where we think that life might have started, places in the deep sea where hydrostatic vents heat water and provide a strange but rich habitat for all sorts of life. And so from an inert ice cube, Enceladus has become a place in the solar system where we think we have a good, well, actually, that's not fair. It's become the place in the solar system where we think we have the best chance of finding other life. Of course, we have to answer questions. We have to answer questions, for example, about whether the ocean is long-lived. Have we been lucky? And actually, we've managed to solve that because it turns out, and this is my favorite shot of Enceladus. Enceladus is the dot in the center of this image. What you're seeing there is the water that's spraying from the moon is feeding into a ring around Saturn. It's called the E-ring. It had been discovered long before any probes visited the Saturnian system. It's the outermost, she's not quite the outermost, it's the most tenuous of Saturn's rings. And it's so substantial that we know that the ocean must have been there and these fountains must have been active for certainly millions of years. And so Enceladus is suddenly this place that could be a habitat. It became a huge focus completely unexpectedly. Cassini hadn't planned to spend any time doing more than taking a couple of pictures of Enceladus, and it's become the major discovery from what was a 17-year mission. And it adds to a picture of the solar system where ice worlds, worlds with water locked underneath thick, perhaps, icy caps, are increasingly common. We see them in Jupiter's moons. We see Europa, the large picture here, and Ganymede in the top right, two large moons of Jupiter, have patterns on their surface that seem to suggest that underneath their icy surfaces, there are also oceans. Even Pluto, pictured in the bottom right there, is seen by the New Horizons spacecraft, which had this heart-shaped feature, now named Sputnik Planeta on it, the smooth area you can see on this picture. A good explanation for why that's smooth is that there's an underwater ocean with currents that are able to replenish the surface. And so, viewed like this, if you ask where the most common habitats for life in the solar system are, the answer isn't in a nice habitable zone, a region around a star where you can exist and wander around on the surface of a planet. It's actually safely locked away under the icy cap of an outer solar system moon. And if that's true, and let's say these places are inhabited, let's say there is bacteria or squid or dolphins or who knows, whatever you want to imagine, swimming around in the oceans of Europa or underneath Enceladus's icy cap, they, if they've reached intelligence, would consider our existence to be horribly precarious. I mean, how can you live on the outside of a planet? You know, you're exposed to solar radiation and cosmic rays and all sorts of things. It would be ridiculous. You can imagine alien astronomers in these moons putting forward really, really convincing arguments that the only places you could live are safely protected from the rest of the solar system. We will look strange to them. Of course, their astronomy would be a bit different. They haven't been able to see the sky. Maybe they've discovered radio astronomy. One can speculate about what scientists in such an ocean world would find, but maybe we'll save that for conversation or questions later. The discovery of habitats on the icy moons of the outer planets of Jupiter and Saturn have broader implications still. When we look up at the night sky, we now know, and this is a completely gratuitous picture of the night sky, by the way, taken by Will Gator. When you look up at a night sky like this, up at the stars that we see in the sky, you should realize that we now know that planets are common, very common in the galaxy. One of the great discoveries of the last 10 years has been the idea that the galaxy likes creating planets, that the physics and chemistry that acted in our solar system, which we don't understand perfectly, but whatever processes acted to produce our solar system, also acted throughout the galaxy. And so if you go outside tonight and look up, then most of the stars that you can see have planets going around them, we think. And therefore, we can ask the question whether some of those planets are suitable homes for life. And there's been an enormous focus, a targeted effort, with dedicated spacecraft and much angst and argument about statistics, to try and determine what percentage of those worlds are Earth-like, in the sense that they might support our kind of life in the kind of habitat that we've become used to thinking about here on Earth. But with the icy worlds, we now know that this is not quite the right question. We have to include not just Earth-like planets in Earth-like orbits, but we might want to include, when we see a star that has a Jupiter-sized planet going around it, we could assume perhaps that such a planet would have moons. We don't know yet. We haven't discovered a moon around another planet for good reason. It's difficult. But we could assume moons are common in our solar system, so maybe they're common elsewhere. And we could assume that we have to add those to the cosmic calculus as well. And when you do that, you quickly get to an assumption that there are hundreds of billions of potential homes for life in the Milky Way galaxy alone. And this creates, I don't know, how are you feeling? Existential dread, something like that? A feeling of aloneness. It adds to what tends to be known as the Fermi paradox, which is this question of if life is common in the galaxy, where are all the aliens? And the book is not, I promise. There's no final chapter that says, and they're here. I thought about it, but one wants to stay close to actual science. We don't see UFOs. We don't see signals bouncing around the cosmos. And so the fundamental mystery, I think, in astrophysics at the minute is that we know that there are places where life could exist, where we have the raw ingredients for the kind of life that we see around us abundantly here on Earth. But we don't see any evidence of life itself. So there are many possible answers to the Fermi paradox, which range from, the depressing. You could pick an answer like the fact that you might believe that whenever a society gains technology, let's say about the level that we've managed, it inevitably destroys itself. Might seem plausible on a bad day maybe, but it's not very cheerful, is it? You could reach for, let's have on the other side, you can have a very optimistic solution. My favorite of the optimistic solutions is called the national park hypothesis, which is that there's a sign a few light years away that says leave them alone until they grow up a bit, that we're a reserve waiting for cosmic maturity, at which point, the wise species of the cosmos will come and give us their secrets. And if science fiction's anything to go by, strange drinks that are mostly blue for some reason. Quite looking forward to that bit. We can have scientific answers. I like the blame the biologist solution. We don't know. I've said there are habitats for life, but we don't know. If I give you a planet or a moon, and say, what are the odds of life getting started given those conditions? We don't know how to answer that question. And so maybe life itself is rare in the cosmos. And we've already won the cosmic lottery by existing at all, that we do face an empty, mostly lifeless cosmos, but our place in it is special. I think we'll put that in the complicated box. I'm not quite sure how to feel about that one. Or maybe life is common, an argument made by Simon Conway Morris, the great paleontologist, who thinks that life will be very common in the cosmos, but intelligence will be rare. So maybe life gets started quickly. You can argue that it got started quickly on Earth, for example. Life appeared very quickly after the Earth reached suitable conditions. But intelligence, which, as ever, I'll define as having professional astronomers and gins and tonic, was reached somewhere in the 18th century by that metric. And so we are new in the cosmos. And perhaps this idea that life will be common, but we won't find anyone to talk to, is the solution. Now, I don't know. I'm not going to answer this paradox this evening. We could keep going and pick many, many solutions, ranging from deciding that it's crucial to have a Jupiter in your system to maybe deciding that the moon is special. But we have looked, of course. If I'm talking about cosmic surprises, the ultimate surprise, I think, would be a signal from an apparently intelligent source. And there are plenty of times in the history of astronomy where, just for a moment, we've thought about whether we might have found such a signal. Usually, traditionally at least, this is the domain of the radio astronomer. I don't have time to go into the history of radio astronomy today, but one of the great joys of the book has been reading up on the history of the, frankly, slightly eccentric bunch of engineers who invented a whole new science, a way of listening to the cosmos, of using technology developed for communication here on Earth and then for radar during World War II, to detect what was originally called star noise, radio signals coming from the cosmos, and the way that they were poo-pooed by pretty much every professional astronomer going, because they didn't use mirrors and they didn't map stars, so what could they possibly know? That's a whole other story. But originally, it was thought for a long while that aliens would communicate with radio. It's a cheap way of sending long-distance messages across the cosmos. And so when Jocelyn Bell Burnell, working on an experiment in a field in Cambridge, covering 57 lawn tennis courts with antennae in order to detect distant sources of light, distant sources of radio waves, and try and determine, in fact, whether they were distant sources coming from distant galaxies or whether they were nearby, found what she described as a scruff on a piece of scruff labeled just over here as CP1919, that little squiggle in the signal coming from her radio telescope. One of the first thoughts of the team, who'd seen this signal that was pulsing very rapidly, several times a second, one of the first thoughts was that this might be an alien signal. And the signal was nicknamed, in a well-known story, it was nicknamed LGM-1, for Little Green Men 1. Jocelyn's written about this in many places, but I really like the story that they were very relieved when they found LGM-2, Little Green Men 2, which was a similar signal elsewhere in the sky, because it was felt implausible that they'd find two sets of aliens sending exactly the same signal, or same sort of signal, and so they thought this has to be something natural. And it turned out to be, these are pulsars, these are the dead remnants of massive stars spinning rapidly and sending radio waves out into the cosmos. It's an early reminder that radio could be used for this sort of SETI, this search for life in the cosmos. These days, we do targeted searches. This is the big dish at Parkes in Australia. I described this earlier today as on the radio as Australia's Jodrell Bank, and managed to offend both Australian and British radio astronomers. So it's its own thing. It's known as the dish. This is the instrument that, in its spare time, carried some of the video signal from the Apollo moon landings to Earth, enabling us to watch that one small step onto the Sea of Tranquility. And one of the things that Parkes specializes in is in looking for things that change in the radio sky, finding rapidly changing sources like pulsars. It was instrumental in the discovery of a surprising new class of object a few years ago, named with, I guess, some economy of thought. These things are known as fast radio bursts because they are fast bursts of radio waves that we see coming from all over the sky. They're interesting. Some of them repeat. A couple of them have been identified as definitely coming from distant galaxies, and there's one that seems to come from within the Milky Way. Sometimes some of them don't repeat, and some of them jump about from different frequencies. And we don't know what these things are. We're currently at the sort of hand-wavy stage, where they may be something to do with magnetic fields, maybe something to do with dead stars, maybe something to do with an exotic form of the same type of object that powers a pulsar. But the search for fast radio bursts also contains within it a lovely story about the need to be careful when you are surprised by the cosmos. Along with the fast radio bursts, there were a set of different signals, which the team at Parkes called peritons, that were seen coming again from the whole sky. So the fact they're coming from all over the sky tells you that they're not coming from the solar system, because the solar system, all the planets orbit in a disk. So we then expect, if you saw them coming from around the zodiac, then you've got a solar system source. We also know, because they're coming from all around the sky, that they're not coming from the Milky Way. Because the Milky Way, if you go out and see it on a dark sky, or if we look at Will's wonderful photo, you've got the stripe of the Milky Way there. It's a disk. So we'd expect things, if these things come from our galaxy, they should follow the Milky Way, but they don't. They come from the whole sky. And they were all at exactly the same frequency. So there's obviously something special about whatever's producing these things that means that they were all at the same frequency, like the same channel on your radio, picking up on these new cosmic sources. The only problem with these things, with these peritons, came when somebody noticed there was a very distinctive feature about them. And that was that they all happened around lunchtime. And if you think about it, distant cosmic sources shouldn't know and certainly shouldn't care when it's lunchtime in Australia. That would be weird or worrying, or possibly both. The mystery resolved itself when a retired engineer saw one of the papers that had been published on these things and knew exactly what it was from the frequency response. It turns out the microwave in the visitor center was malfunctioning. In particular, if you obeyed manufacturer instructions, all was well, but if you were impatient and opened the door before it had pinged, it didn't shut off straight away. It, in fact, generated a source of microwaves that could be picked up by the radio telescope. So we can create cosmic signals using a microwave. The fun thing is that there's a story which I desperately tried to pin down for the book and couldn't get anyone to tell me on the record. So you can choose not to believe this, but I know of at least 2 people whose summer projects at radio observatories around the world involved trying to break microwaves in the correct fashion so as to generate peritons. And I love this idea. Imagine turning up, you're 20 or something, you're a university student, you've got summer doing research at insert name of radio facility here. You're going to discover things about the cosmos, and you're given a microwave and a hammer. I think, now we're talking about how science is really done, I think. I'm sure those people learned lots. But this idea of needing to be careful is, of course, crucial. The other image on this slide is an artist's impression of a planet around Proxima Centauri, the nearest star to the sun. And one of the great joys of doing SETI, of looking for aliens at the minute, is that we know now where some of our nearby planets are, and it seems that our nearest star has planets going around it. And so we can concentrate our search on places where we know there might be places where there might be life. Indeed, Parkes in 2019 picked up what appeared to be a signal that was consistent with what you'd expect from a transmission coming from a planet around Proxima. It moved in the way that we'd expect a planet around this star to move. This was part of a search for alien signals called Breakthrough Listen. And the signal was given the name BLC-1. We've moved on from LGM. BLC, Breakthrough Listen Candidate 1. And the team set about trying to find out what it was. It seemed real. It seemed to come only when the telescope was pointing at Proxima and not when they pointed elsewhere. By the time they found it in the archive data, they went back, it wasn't there anymore. So it may have been a one-off. And at this point, it leaked to The Guardian. Ian Sample at The Guardian got hold of the story and wrote it up. And they were very cool. Aliens, not aliens found, but astronomers have signal which maybe, possibly, could be once we've ruled everything else out. It was an excellent piece of science writing. The team, I think, were quite annoyed that their possibly, maybe had escaped into the world. The thing is that once they'd found the signal, they were able to reverse engineer it. They went looking for things in the data from Parkes that looked the same as the signal. And they found many, many, many of them from all over the sky. It may not have been a microwave, it was probably a malfunctioning satellite, but it's not aliens. And actually our search, despite these habitats, as you'll know from the paradox that I brought up, hasn't found us any alien radio signals. But instead, we've started to think about other ways we might detect life, other ways we might be surprised by life in the cosmos. I got involved in this myself by accident. One of the things I do with my team in Oxford and with volunteers online via the Zooniverse Citizen Science platform is look for planets. This is part of the evidence that backs up the thing I told you 15 minutes ago, that most stars have planets going around them. We can't see the planets directly, but we can detect their effect on a star. So this is the sun, which you'll remember from last year. And this is a video from 2012 where Venus passed in front of the sun, something that happens as seen from Earth only twice a century or so. And what you can see on the left is the nice image, and on the right is the even better graph showing the transit. And the graph just shows the brightness of the sun over time. We just took a light meter out into the university parks in Oxford. And what you can see, and this is one of the things I really love about this, is this measurement will go on to have deeply profound consequences, but it's wonderfully simple in astronomy, okay? The basis is when a planet is in front of the sun, you see less of the sun, so it gets a bit fainter. Right? That's as sophisticated as if I hold my finger in front of a light bulb, I see slightly less of the light bulb, right? But you can tell that the finger is there. You can tell that the planet is there from the dip, and hopefully you can tell how big the planet is, how much of the star it's blocking, and maybe if you're clever, you can start to work things out about its atmosphere. So this is the game, and what we do is we take data from we used to take data from a NASA satellite called Kepler. We now use a NASA satellite called TESS. Put the data online. You can go to planethunters.org and sort through that data and look for these dips that tell us that there are planets there. Every month we get to email people and say, we think you found planets. It's great fun. I highly recommend it. It does mean looking at graphs in your spare time, but I think you're okay with that. Let's look at some graphs in our spare time. I particularly want to show you this one. This is the data that we had for what turned out to be a very, very interesting star. So this is a star that has gone through many names, but when we started looking at it, was known as KIC 8462852, which you'll know intimately, I'm sure. And this graph just shows the brightness over time as seen by the Kepler satellite. You can see that just after we started monitoring it, there was this dip in brightness. So that could be a big planet getting in the way of the star. And in fact, it repeats. So now we know that we think there could be a big planet and it goes round every couple of months. But actually, there's no third dip. There's no third transit. And planets don't take breaks, right? You can't have a planet that goes round and then stops for a bit. So whatever's causing these dips isn't a normal planet. Didn't think too much about this until about a year later, where our volunteers noticed that there was a very big dip. Only in the Royal Institution you get gasps of wonder from a graph. This is brilliant. You are clearly my people. This is great. But it is dramatic. You were right to gasp. It's a 20% dip in brightness that lasted maybe a week or so, and then the star came back to full brightness and carried on as if nothing had happened. Stars don't do this. Quantitatively, none of the other 190,000 stars studied by Kepler in its main sample ever did this in the 3-year mission. At this point, it was noticed by our volunteers who started wondering about it, and then they really started wondering about it a year later when it did this. I don't even have a technical term for this other than went on the blink, I suppose. The volunteers got very interested in this. They called it the WTF star. And started coming up with ideas as to what might have happened. They suggested that maybe there was a dust disk around the star that was blocking out some of the light. We looked in the infrared, there's no glowing dust, so we ruled that out. We started getting paranoid. We spent ages doing things like working out which pixel on the camera the star's light was landing on, in case there was a duff pixel somewhere. We checked neighboring stars. We checked the star with other telescopes. It's a perfectly normal middle-aged star. It shouldn't be doing this. It was really confusing. And eventually we just wrote a paper, which we submitted to the journal with our volunteers as well, led by Tabby Bourgeon, who's now at Louisiana State. And we said, we don't know what this is. We found a weird star. It was great. It was really good fun. This is the kind of astronomy I get excited about. And the journal editor wrote back, and we got quite a good report, and he said, look, the paper's okay, but there's 2 problems. Problem number 1 is that you've called this the WTF star. And our rule is that all acronyms have to be spelt out in full. So WTF stands for where's the flux? Not my joke, but it's excellent. That actually came from one of the volunteers, so that's good. If you don't know why the older people in the audience are laughing, that's fine. Second thing is they said you can't, and I disagree here, they said you can't just say it's weird, you have to have a hypothesis, right? Because that's how we pretend science is done, right? We have a hypothesis and we test it. So we scratched around and said, okay, the best idea we've got is that there was a comet in orbit around this star. Comets are icy bodies, we see them in the solar system, they swing into the inner solar system, and sometimes when that happens, it's happened to some very famous comets over the years, they break up into bits. The bits, by the way, are called cometlets, which is one of my favorite facts. And so we said, okay, so what's happened here is a comet has swung in towards the star, it's broken up, and we have a string of comet bits, and every time a comet bit goes in front of the star, we get a dip. Bigger ones cause bigger dips and so on. And we created an unconvincing artist's impression of exactly such a system. There you go. Apologies to the artist. And we said, okay, this is our explanation. And immediately, you'll be ahead of me, perhaps, that there are a couple of problems with this. One is that I can explain absolutely anything with this idea, because I can arrange my bits of comet however I like. So does that count as a proper scientific hypothesis? Not sure. The other thing that happened was that people who know about comets got quite angry with us, because we know quite a lot about comets. We know, for example, that they're typically a few kilometers across. Here's a scale model of comet Churyumov-Gerasimenko, the target for ESA's Rosetta probe, menacing the city of London. It's about, it's a few kilometers across. We would need the largest comet ever seen by a factor of about 10,000 to have just broken up just before we happened to look at this particular star, and that only to have happened around this star and not any of the others that we were looking at. So we were asked sensible questions like, how are you forming this big comet then? And so on. So we abandoned the comet idea, and other people started putting forward ideas. The most prominent of them was a group led by Jason Wright at Penn State, who put forward an idea in the main astronomical journal, the Astrophysical journal. He said, look, maybe this is an alien megastructure around the star. That what we have is not a comet, but what's causing these dips is the construction of a set of alien solar panels. Because surely an advanced civilization would get its energy from orbiting solar panels in orbit around the star. Obviously, they've constructed large panels, they get in the way of the star, and they block the light, and that's what we're seeing. I think, to be fair, they said we should consider this hypothesis. The media considered this hypothesis in great detail. I found out about it when I picked up my phone on a Monday morning, and this voice said, hello, this is somebody from the Daily Mail. I hear you've discovered aliens. I hadn't had coffee. I genuinely said, I don't know, I'll check my email and see if we have. I'm going to show you, I've got a collection of front pages, but I really like the Independent, because they're the only people who use the word may have discovered, which was nice. Is this a good idea? Had we discovered aliens? Well, it's got the same, you can criticize it the same way you can criticize our comet hypothesis. You can arrange your alien solar panels however you like. You can explain any pattern this way. Nonetheless, we'd like to rule it out. So we devised a program of observations. We kept an eye on the star using a network of telescopes like this one on Maui. This is the LCOGT network, LGOCT, one of the two, network of robotic telescopes. And every time it was clear, they kept an eye on what's now known as Bourgeon's star. Sadly, the W2F star didn't catch on. And we waited for it to dip again. When it did, we used an advanced communication network to alert astronomers around the world. And people, amateur astronomers, professional astronomers, rushed to observe the star for us. And this time we got a crucial observation. What we saw was that if you looked at the star with cameras that were sensitive to different colors, so if you looked, for example, in the red here with a camera that was sensitive to red light and one that was sensitive to blue light, shown in blue, you can see you get a dip in brightness both times, but they're different depths. So the amount of dimming depends on color. What that tells you is that this isn't a solid object blocking the light, because a solid object would block all colours of light equally. So no alien solar panels, I'm afraid. We did run the numbers for alien solar panels with Christmas lights on the back, and that doesn't get you out of this. It's probably a cloud of dust in orbit around the star. And I don't have time to tell you the rest of the story, but I think today in particular it's worth talking about where that dust might have come from. Because in the news today, in Nature this morning, there is a story that says at least 1 in a dozen stars shows evidence of planetary ingestion. So this is a story about planets eating stars. And this is hot off the press. It's a really clever study, actually. I'm going to do what they did. It's a bit dry, so there's the paper and there's some quite technical text and some graphs. But they provided an unconvincing artist's impression as well. So let's do that. There we go. Clearly, that's what a star eating a planet would look like. Let's go with that. But the study's really clever. What they did was they took binary stars, pairs of sun-like stars that are in orbit around each other. And we think that these stars will have formed together in the same place, made from the same material. And so they should have the same composition. Most stars are mostly hydrogen, but they have trace elements from carbon and oxygen, nitrogen, and all the rest. So the two stars should have the same composition. And what they did was they studied about 50 of these pairs, and they found that in 7 or 8 of them, I mean, it's 7 or 8, I just can't remember which it is, but you get the idea. There's a significant difference between the two. One of the stars has more stuff that isn't hydrogen. And the hypothesis is that that difference can be explained by that star having consumed a planet or so, and done so while it was in its sedate middle age. So this is interesting. It's a nice quirk of nature, maybe, small n. But what it made me think about was the stability of our solar system. If these systems are eating planets, are we safe? Like, are we okay? Now, I should say that this is breaking news, and so half an hour ago I saw a response to this survey by an astronomer called Sean Raymond, who knows about these things, who pointed out that we probably shouldn't worry from a solar point of view, because these are double stars. There are 2 stars in orbit around each other, and they're quite a long way apart, each of these systems. And that means that the stars are affected by galactic tides. They feel the gravity of the rest of the galaxy. And so every so often these stars, the orbits aren't quite stable. They will move relative to each other because they go through a spiral arm or so on. And if you move a star around, you probably disrupt a planetary system. So maybe we don't have to worry. But it turns out that when you think about our solar system, we should be, I think, slightly surprised that it seems to have been stable for the last 4 billion years or so. There were some studies about 10 years ago that ran computer simulations of the major planets and the sun in our solar system. And we understand if you just have the sun and a planet, and the planet's in orbit around the sun, things are fine. The planet just goes round and round and round until the sun dies in about 5 billion years' time, which is a long-term problem that we won't consider this evening. Once you add in a couple of planets, their gravity starts to mutually interact. The Earth is pulled not just by the sun, but by Jupiter, to a lesser extent by Saturn, and indeed even by Venus and Mars. Even though they're small, they're relatively close. And calculating what happens in the long term becomes difficult. This is a chaotic system. The experiments that were done about 10 years ago showed that this system often went haywire, that Mercury flew off its orbit, disrupted Venus, Mars, disappeared into the sun reasonably often. And it was actually quite disturbing, because if you can't predict that we were going to be stable for the next billion years, you have to ask whether it's weird that we've been stable for the last 4. So either we're lucky, or there's something about our solar system that means we're prepped for long-term survival. And actually, recent work has shown that actually the precise configuration of the planets in our solar system, the presence in particular of a large Jupiter-like planet in a Jupiter-like orbit, means that we are sitting pretty, that there's only 1 in 2,500 chance that Mercury will do something odd in the next billion years. So having made you worried about the instability of the solar system, I now want you to relax. It's all fine. We're not going anywhere. But there's another type of accident here as well. I think the fact that we find ourselves in this solar system, we don't know which bits of what we see are genuinely just a roll of a dice. For example, I'd bet that there's nothing special about the fact that we have 8 major planets and Pluto. Pluto, not a major planet. We can argue about that later if you like, especially people watching online. But my guess is that the solar system would be fine, that we'd be just as habitable as a planet with 7 or 9 or 10 or 14 or 6 major planets. But maybe it's important that Jupiter's where it is. For starters, it catches lots of asteroids that come in towards the center of the solar system. Maybe it's certainly important that we are where we are on our habitable zone. If we were closer in, things would be different. One of the stories that I tell in the book is a story about conditions on Venus. Venus should be Earth's twin. It was about the same size as the Earth, formed in the same part of the disk as the Earth, presumably, and yet it couldn't be more different. It's a place with a thick atmosphere of sulfuric clouds, with an atmospheric pressure that would crush you, an atmosphere that would dissolve you. It's so acidic. It's about the same acidity as sulfuric acid on a school lab bench. And it has it's the hottest place in the solar system, so you'd also melt on the surface. It has active volcanoes, no plate tectonics. It's a very strange place, and yet recent results have shown that from this telescope, the James Clerk Maxwell telescope in Hawaii, that high in Venus's atmosphere, there's a layer where conditions are a bit more temperate, where it's still acidic. Don't go there on holiday. But it's sort of balmy, Earth-like temperatures of about 20 degrees centigrade, Earth-like pressures, and in that layer, a remarkable woman called Jane Greaves from Cardiff and her team have shown that there's a chemical called phosphine present in the atmosphere. And that phosphine is interesting because on Earth, only life produces phosphine, counting us and our factories as life, but it's not produced naturally. In fact, a major source of it on Earth is in penguin poo, and it's been used to detect penguins from space. You can count how many penguins there are by detecting the phosphine on the ice in their poo. Didn't expect that from an astronomy talk, did you? So, phosphine is what we call a biosignature, a chemical whose presence appears to betray the presence of life. Now we found it in the atmosphere of Venus. Does that mean there are penguins in the atmosphere of Venus? Any question, any title, any statement that has a question mark at the end means the answer is no. So I don't think there are penguins, but could there be phosphine-producing bacteria there? Potentially. We don't understand the chemistry of Venus's atmosphere enough to answer this question definitively. But if there is life high in the clouds of Venus, then one way to think about it is it's the last vestiges of what would have been a very hospitable planet. Early in the days of the solar system, Venus would have been a second Earth. It would have been temperate before there was a runaway greenhouse effect. You can imagine life developing on the surface to the same extent that life developed here on Earth. You imagine a rich biota of fill in whatever you want to imagine on Venus. Let's have Venusian elephants and palm trees today. Why not? But, pick your own species. And then the planet warms up. It, through no fault of its own because it's close to the sun, has this runaway greenhouse effect. And the bacteria that might be producing phosphine high in the atmosphere would be the last remnants of life clinging on in the last habitable place on the planet. And when you think about that, and then you come back and look at the Earth, you realize the accidents that have led to us being here. And I write in the book about the fact that once you start realizing that we're not doing hypothesis testing and exploring the cosmos, you end up thinking about the fact that there's a historical story to tell about how we ended up here on Earth as beings that are capable of contemplating the cosmos. And you can work backwards from the fact that it was probably good for us that an asteroid happened to collide with the Earth off the coast of Mexico and do for the dinosaurs so that scurrying mammals could flourish and end up producing us. It was good for us that the moon exists, something the size of Mars hit at the Earth 4.5 to 5 billion years ago, creating the moon, which stabilizes our axis, may have played a crucial role in providing tidal spaces on Earth so that land-based life could develop. It's lucky for us, perhaps, that Jupiter exists, as I've already mentioned. And we may even go back to the fact that the only reason the sun exists is because a small galaxy collided with the Milky Way about 6 billion years ago, triggering a burst of star formation that led to a supernova, which sent shockwaves rippling through this part of the galaxy, which triggered a burst of star formation that may have included the sun. So we may owe the fact of the Earth's existence to a particular collision with a neighboring galaxy. We have a historical story to tell about why we're here, as well as explaining the physics and chemistry that led to the processes that powered that supernova, that produced that star, that formed that planet, that caused the formation of the moon, that meant that the asteroid hit us. There's also this sort of historical story. And I think we can bring both of those things together when we look out at the universe. So I want to finish with one final story of an accidental discovery. This is my favorite. Started with my editor's favorite, and we'll finish with my favorite. And it's to do with this thing, which is my favorite telescope. This is, of course, the Hubble Space Telescope, the first great observatory, planned since the late 50s, launched into space in 1990. The whole point of Hubble was to get above the Earth's atmosphere, to get away from the pesky interference that we astronomers have put up with for too long of the atmosphere that, yes, we enjoy breathing like the rest of you, but it is a nuisance. When you go out and look at stars twinkling, they're not supposed to do that. And it's intensely frustrating if you're trying to take sharp images of the night sky to look up at the stars and see them moving around. So the point of Hubble was to get above all that, to get crystal clear images of the sky. Hubble's not a particularly big telescope. It wouldn't have been the biggest telescope on Earth in the 1950s. But because it's in space, it was designed to have the sharpest resolution that had been achieved. And so it was a disaster just after launch when it turned out that Hubble's images looked pretty much like those you'd get from similar telescopes here on Earth. This is the first image that was sent back. This is Hubble on the right, and a ground-based telescope, I think in California, on the right. These are two telescopes the same size. And you might be able to see that maybe Hubble is slightly sharper, but it's not expensive billion-dollar space telescope obvious. This was a disaster, and it got worse as it became clear that this sort of problem, this blurred vision, was affecting all of Hubble's instruments, which meant that it was a problem not with a particular camera, but with the Hubble's main mirror. It had, in fact, due to a washer no more than 1 millimeter thick that was in the wrong place on a piece of testing equipment, it turned out, the mirror had been precisely fashioned to the wrong shape. In an act of precision engineering that was utterly misguided, the team had kept grinding the mirror until it was just ever so slightly the wrong shape and produced this blurred vision. A fix was needed. NASA couldn't afford to wait. And I should say, I always say NASA here, but Hubble is a Canadian, European, and American mission, so we should take some of the blame and credit as well. We actually caused our own problems with the solar panels, but that's a whole other story. NASA couldn't afford to wait to build new cameras with adjustments built in, and so they built this remarkable thing called COSPAR, which looks, it's on the right here, on the left here, which looks like a sort of set of dentist tools. Had all of these little mirrors that stuck up. It was installed by astronauts from the space shuttle into Hubble. All these mirrors popped up, and they corrected its vision. So it's like fitting glasses to 3 cameras simultaneously. This was a remarkable mission. It was intensely complex. It involved fixing bits of Hubble that were not supposed to be fixed by astronauts wearing gloves that made it hard to manipulate things. It was a remarkable piece of engineering and human ingenuity, and it worked brilliantly. So this is now Hubble before and after the repair. This is a famous nearby galaxy. You can see the sharpness of the new images that were achieved with COSPAR that we were able to see. And so the first few years after the fix, from 93, I think, to 95, astronomers from all over the world clamored to use Hubble. Its team worked hard to get back on track, to do the science that it was supposed to be doing, and to keep everyone happy. Now, one of the things that people wanted to do with Hubble was to stare into deep space. In particular, astronomers had identified a place that they wanted to stare. This is the northern night sky as seen from the UK. Many of you might recognize the plough. And there's a small patch of sky. It's about a 24 millionth of the sky, which is about a pinhead at arm's length, that lies here, that has absolutely nothing of interest within it. No stars, nothing. And the idea proposed was to point Hubble at that patch of sky and then wait and try and see the most distant galaxies ever seen. And this was considered a ridiculous idea for two reasons. One, we've just repaired your billion-dollar space telescope. Why do you want to point it at nothing? Are you trying to create a metaphor? You know, it's not good PR. But secondly, eminent astronomers argued that if you assumed that the distant universe was like the universe that we see around us, then Hubble would discover no new galaxies. And therefore, this was a pointless observation. So we did it anyway. But only because of one man. There was a guy called Robert Williams who directed the Space Telescope Science Institute that still runs Hubble. He was the director. He gets a little bit of telescope time in his personal gift. He can do whatever he wants with Hubble that's safe for the telescope. You're not allowed to point it at the sun, for example. He also had a problem, which was that his team were incredibly tired after rushing to get Hubble back up and running. And so over Christmas in 1995, he decided to do the simplest possible thing, to point Hubble at the same patch of sky for 100 hours, to allow his team to take it easy for a bit and see what they could see. And the result of that was that this tiny patch of sky was transformed into a field of about 10,000 distant galaxies. This is the Hubble Deep Field. There are 4 stars in this image. Everything else you can see is a galaxy. And these galaxies are so distant that their light has been traveling towards us for more than 10 billion years. And so we're looking at the early universe here. This became something Hubble did. Here's an extreme deep field, which is a very similar thing. Again, you're looking at galaxies as they were in the first couple of billion years of cosmic history. And the mistake that we'd made was assuming that that early universe would be like the one we see around us today. It turns out it's much more interesting. It's an early universe filled with fireworks, with dramatic star formation, with collisions between galaxies, with black holes eating material at a rate that hasn't been surpassed since. The early universe is full of fireworks, and it surprised us to see them, but they were revealed by taking a punt on an observation that most people didn't think would work. It's about as far from the school textbook method of science as I can imagine. There's no hypothesis here. It was let's look and see what we've got. It's a pattern that's been repeated. The new toy, the JWST, the Just Wonderful Space Telescope that launched a couple of years ago, with its golden mirror tuned to the infrared, one of the first things it did was to look at the distant universe. And this is a nice galaxy cluster, but the interest here is in a set of faint red dots. Galaxies captured as they were just a few 100 million years after the Big Bang. And once again, I and my colleagues have been surprised by the fact that the early universe is not like the one around us today, that it's full of fireworks, of more star formation, of galaxies forming earlier than we anticipated. Wherever we've gone in the cosmos, whenever we're trying to discover and understand life in the solar system, from the clouds of Venus to the fountains of Enceladus, whether we've tried to explore the Milky Way galaxy, to find weird stars like Borodin's star, which is still the WTF star to me, or when we've looked out to the distant universe, whether we've used radio astronomy or optical telescopes, particles or gravitational waves, ripples in space, to look at the cosmos, We've always been in our best as astronomers when we've been surprised and discovered that we live in this accidental universe. Thank you very much.